Hello, everyone. Thank you for coming to my presentation. My name is Hongzhou Liu. I'm from Iowa State University Chemical and Biological Engineering Department. The topic I'm going to present today is paired flow electrolyzers for furanic compounds conversion to valuable chemicals. As we can see, fructose, which is a carbon-6 sugars, and xylose, which is a carbon-5 sugars, are the most abundant biomass-derived sugar and have received great attention as a feedstock for renewable fuels and chemical production. They can be catalyzed dehydrate to HMF and furfural. HMF and furfural have been listed as one of the most top promising platform chemicals, which identified by the DOE. Specifically, selective hydrogenation of the aldehyde group in HMF and furfural will yield some value-added chemicals such as furfural alcohol and the BHMF. The oxidation of the HMF and the furfural will get acid chemicals such as FDCA and furic acid. Conventionally, we only focused on half desired electrocatalytic reaction, and the paired reaction was just oxygen or hydrogen evolution reaction. The produced gases were just released back to the atmosphere without any values. Ideally, if we pair valuable half reactions of both cathode and anode in one cell by using renewable electricity, a theoretical 200% charge efficiency can be obtained. This almost doubled the conventional unpaired cell, and we can co-generate value-added chemicals simultaneously. For the cathode side, we can reduce HMF to BHMF. This BHMF is alcohol that can be used as a precursor for polyesters and resins. For the anode side, HMF can be oxidized to acid FDCA. This is a feedstock to make renewable polymer such as PEF. Here is the experimental setup for paired electrolysis. This figure showed the conventional H-type cell with a membrane separated the cathode and anode. For the paired electrolysis, the cathode can be electrocatalytic hydrogenation of HMF to BHMF, which need 2 electrons. And the anode side is HMF oxidation to FDCA, which is a 6-electron reaction. The overall reaction is from HMF to both BHMF and FDCA. Faraday efficiency is defined as the ratio between the electron transfer to a product divided by the total electron transfer, which means the percentage of charge goes to the desired product. We have designed 2 kind of flow reactors for paired electrolysis, including a 3-electrode-based flow cell with a spacer and a membrane electrode assembly-based flow cell, which is a 2-electrode system. The advantages of using flow reactor instead of H-type cell to perform paired electrolysis, including firstly, it will reduce the capital expense, minimize energy consumptions, and simplify processing steps. Secondly, it will increase the mass transport limitation. Here, I'm going to introduce 3-electrode flow cell first. The 3-electrode flow cell composed of a working electrode, reference, and a counter electrode. The half cell voltage between working and reference can be controlled and monitored. The cathode flow chamber for liquid flow in and flow out. And the reference was inserted to control the half cell voltage. The advantages of using this kind of reactor is that we can use some state-of-art metal foil-based catalyst in this kind of reactor. such as oxide-derived silver, oxide-derived lead, because this catalyst can increase the surface area and bring some subsurface oxygen to increase the catalyst performance. Secondly, we can control the half cell voltage to increase the product selectivity and activity. And we can see the BHMF selectivity is highly dependent on the potential. So by using this kind of cell, we can negatively shift the half cell potential to increase the BHMF selectivity. Thirdly, we can perform some potential dependent mechanism studies in this reactor. By using the state-of-art oxide-derived silver catalyst, we perform the electro reduction reactions at the controlled potential of negative 1.25 volt versus silver chloride. And indeed, we can say there we observed higher BHMF selectivity than silver foil. When applied the oxide-derived silver in the 3 electrode flow cell, we can see there is a further increase in the BHMF selectivity, HMF conversion, and these results benefit from the good design of the reactor that can faster diffuse organic molecules to the catalyst surface. So when we perform the long-term electrolysis in the 3 electrode flow cells with different applied half cell potential, oxide-derived silver maintained a high BHMF selectivity over 80%, and the BHMF conversion can attain almost 90% for 3-hour test. We then did some thermodynamic analysis of the paired electrolysis of HMF. After replaced the anodic oxygen evolution reaction by HMF oxidation, we can say there is a large decrease of the thermodynamic cell voltage between from 1.11 volt to 0.33 volt. For the electro oxidation of HMF, we use a TEMPO as a mediator, and the HMF oxidation pathway goes through the possible 2 pathway. From experimentally, we can see for paired electrolysis, by replacing the anodic oxygen evolution reaction by the oxidation of HMF, we observed a decreased cell voltage from 2 volt to 1.5 volt at the current of 5 milliampere. So obviously, right now we can obtain both high selectivity and high conversion for HMF reduction to BHMF and HMF oxidation to FDCA. So it is ready to perform paired electrolysis in the 3 electrode flow cell. We first use the constant current test in the flow cell. The light blue is the Faraday efficiency of BHMF in the cathode, and the green is in the column is the Faraday efficiency of FDCA in the anode. We can see no matter in the H-type cell and the flow cell, the combined Faraday efficiency has attained over 160%. So more interestingly is that we can see the cell voltage. We compare the H cell and the flow cell. There is a suddenly dropped cell voltage from around 7.1 volt in H cell to around 2 volt in the flow cell. The significant reduced cell voltage was because of the significant decreased resistance. We can say the resistance between working and counter electrode has reduced from over 400 to only 40 ohm. Alternatively, the anodic hydrogen oxidation reaction can be another good substitution for oxygen evolution reaction in order to reduce the cell voltage. We have demonstrated hydrogen oxidation reaction on platinum catalyst and paired with HMF reduction on oxide-derived silver in the flow cell. We can see at the current of 10 milliampere, the cell voltage is only around 9.9 volt. This is because of very phasal kinetics of hydrogen oxidation reaction on platinum catalyst. So the overall cell voltage was consumed by the solution resistance and overpotential for HMF reduction to BHMF. Then we demonstrated a membrane electrode assembly based flow cell, which is a 2-electrode based system. Compared with the 3-electrode flow cell with a spacer, in this kind of cell, there are some benefits, such as it will minimize the cell voltage due to the unique zero gap configuration. And also it is flexible to various GDE-based catalyst and different reaction architectures, like different membrane, pH asymmetric architecture, and it will benefit for long-term stability test. Now we can perform HMF paired electrolysis in the membrane-based flow cell in a pH symmetric structure first. We used both cathode and anode at pH equal 9.2 in the buffer solution. We have performed 24 hours stability test in the three widely used membrane, like anion exchange membrane, cation exchange membrane, and bipolar membrane. We can see the cell voltage has minimized and stabilized to only 1.5 volt in the anion exchange membrane and the cation exchange membrane system for 24 hours. And the performance showed over 130% total Faraday efficiency to the desired product. In all above paired electrolysis system, we use the tempo as a mediator in the anode side, but the use of tempo will induce some separation problem and handle the real application. Therefore, we prepared electrodeposited nickel ion oxide to perform HMF oxidation in alkaline system. Then we use a pH asymmetric structure to match the optimized reaction conditions for both sides. For the cathode side, we still use the pH 9.2, and anode side we use the pH 13. And we can say in the pH asymmetric architecture by using Nephin and bipolar membrane, Nephin membrane system showed a lower cell voltage, but it's not very stable, especially for long term. But bipolar membrane is showed a very stable cell voltage at around 2 volt, and the total Faraday efficiency in these two systems showed always 120%. Finally, limited by the mass transport of most organic-based chemicals, we designed a tandem electrocatalytic system. Especially at high current density, we cannot fully avoid the hydrogen evolution reaction on the cathode side. So we proposed that the hydrogen evolution produced hydrogen can be purged into a second battery reactor for catalytic hydrogenation of some organic feedstock to valuable chemicals on palladium-based catalyst. So by this kind of demonstration, we in the first MEA-based cell, we can say we achieved a BHMF Faraday efficiency of 24% at a very high current density, around 280 milliampere per centimeter square. And the sad reaction produced hydrogen was purged into the battery reactor and get a high production rate of benzyl alcohol and sulfur alcohol production. So then I got some basic conclusion from my project. Firstly, we demonstrated a 3 electrode flow cell for each MF paired electrolysis with oxide-derived silver as cathode, and achieved very high selectivity. Secondly, we designed membrane electrode assembly flow cell in both pH symmetric and pH asymmetric configuration. And thirdly, we achieved a combined Faraday efficiency of over 160% and minimized the cell voltage of only 1.5 volt. So a further optimization of the cell is required to further increase the efficiency and activity. Lastly, I want to thank you, my major professor, Dr. Wenjun Li, and my group members. And I want to thank the NSF to support our research. Thank you.